So now we use the new centroids to compute the Euclidean distance of each object, as you can see in the table. And now the new clusters contain only points 1 and 2, and cluster 2 includes 3, 4, 5, 6, 7. So point 3 switched from cluster 1 to cluster 2. And these are the two centroids. So individual 3 was initially placed in the wrong group because our starting centroids were far from ideal. After one update, the centroids shifted to better represent their groups, and individual 3 found its true home. Now we run the distance calculation one more time, and now we get these two new centroids. And looking at the table, every individual is already in the correct group. So no point is closer to the other centroid, so we stop the process. So this is called convergence, and the algorithm will stop. And our final clusters are cluster 1, which includes only individuals 1 and 2, and cluster 2, which contains 3, 4, 5, 6, and so on. So in this example, the algorithm took just 2 or 3 iterations to converge on a very clean and intuitive solution. And that's exactly what we want from k-means clustering. So you can see here cluster 1 and cluster 2. So you can see that two clear groups, small cluster in the lower left containing individuals 1 and 2, and a larger cluster in the upper right with individuals from 3 through 7. Even looking at the raw scatter plot with no algorithm at all, most people would draw their boundaries at about the same space, right? If I didn't give you these two clusters, you would say, oh, these seem to be the two natural patterns here. K-means has successfully discovered this natural structure, but it did it algorithmically, with no human guidance about where to draw the line. This is the visual intuition behind k-means. The centroids act as magnets, and the data points organize themselves around those magnets until the system reaches equilibrium. Now, if we take the same data, but this time we say we want 3 clusters instead, so you will see how the output dramatically changed just as a result of changing the number of clusters you're starting with. So using these two updated centroids, if we go through the same process, we end up with 3 clusters. Okay, so you can see that 2 very small clusters at the bottom left, essentially individual 1 by himself, individual 2 alone, and then the large cluster on top stays unchanged. Now, is that a better result than k equal 2? Well, it depends on the context and your domain knowledge. But from a purely visual standpoint, splitting 1 and 2 seems to be an overfit situation. They're very close together and arguably should belong to the same cluster. So this illustration shows one of the key challenges in clustering. There's no single right answer. The algorithm will always produce k clusters, but whether those clusters are meaningful in a judgment call is a judgment call that requires understanding of the data. Here's another example. In this case, we have real-life medical data set. Again, you will see how clustering works in practice. So we have 4 medicine, A, B, C, and D, each described by 2 attributes, weight index, and attribute 2 is a pH level, and you have the values you can see in the table. Our goal is to cluster them again in 2 clusters. So we repeat the process, and you can see that we're going to converge to since we're not changing the process. We're going to converge into these two clusters. Okay, so if we keep going with the process, we can see that once this is the code for doing this, and you will end up with two clusters. Now, no algorithm is perfect, and k-means has some well-known weaknesses that you need to be aware of when applying it in practice. Weakness 1 is its sensitivity to initial conditions. When the number of data points is small, the initial random placement of centroids can have a large influence on the final clusters you get from the algorithm. If you run the algorithm 10 times with different random seeds, you might get 10 different results. The second weakness is that you have to choose k in advance. This is probably the biggest limitation of k-means clustering. In real-world datasets, you often don't know how many clusters exist in the data. And techniques like the elbow method, where you plot the loss function j against different values of k and look for a kink in the curve, can help, but there's no foolproof rule. Weakness number 3, order sensitivity with small datasets. If you feed in the same data in a different order and the dataset is small, you may get different clusters. This is because the initial centroid choices depend on order in some implementations. Number 4, local optimize. So k-means converges to a local minimum of the loss function j, which is not always the global minimum. So to mitigate this, a common practice is to rerun k-means multiple times with different random initializations and keep the results with the lowest final loss function j. Now, let's talk about why k-means is so widely used. First reason is efficiency. K-means computed in order of magnitude t times k times n. Okay, where n is the number of data points, k is the number of clusters, and t is the number of iterations. So this is linear in n, which means it scales well even to large datasets. Compare that, for example, to another clustering approach like hierarchical clustering, which has time complexity of n squared. Okay, so it takes much longer. The second is machine learning and data mining. So k-means is used as a pre-processing step to reduce the complexity of a dataset. For example, finding representative prototypes for each cluster and then training a classifier on those prototypes rather than the full dataset. Third, speech recognition and audio processing. In a technique called vector quantization, continuous audio waveforms are converted into one of k discrete categories, and this is essential in voice recognition and voice recognition systems. Fourth, in image compression and color quantization. In the early days of computer graphics, display devices could only show a limited number of colors, so k-means was used to select the best k colors to represent an image, dramatically reducing file size while preserving visual quality. Modern image compression still uses a variation of this idea.